Good evening, everyone. We are Group 8, and today we are presenting our project titled Strategies to Improve Classification Accuracy of the IRIS dataset using Random Forest and J48 Decision Tree Machine Learning Model. So, before diving into our project, let me introduce the team members. So, myself, my name is Katyayani Selvaraj, and my metric number is DI220145.
My name is Tami Arasi and my matching number is DI220133.
My name is Harini Anandara and my entry number is DI220138.
My name is Chandra Nidata Samragarja and my matrix number is DI220174.
My name is Nurul Nadira binti Abdurrahman and my metric number is DI220133.
So now that you know a bit about each of us, let's move on to the project itself. So our project explores the strategies to improve the classification accuracy on the IRIS dataset using two powerful machine learning models, which is random forest and the J48 decision tree. So I will be begin this presentation with the introduction. So decision support system, which known as DSS, help in making better decision by using data and machine learning. This system improves the decision making by recognizing patterns and making predictions. With advance in machine learning, DSS has become even more powerful, handling complex data to provide strong support in critical decision. This study aims to improve the classification accuracy of the IRIS dataset using two popular machine learning models, which is random forest and J48 decision tree. The IRIS dataset classify three types of iris flowers based on four features, which is sepal length, sepal width, petal length, and petal width. However, the dataset has challenges like overlapping features which need specific techniques like hyperparameter tuning and data pre-processing to get better results. By tackling these challenges, research will add to the growing field of using machine learning models in DSS, showing how techniques like pre-processing and model optimization can improve accuracy and make DSS more reliable for decision making. I shall pass the presentation to the next team member.
Thank you, Yani. So I shall now continue with the literature review of our project. So in this topic, there are a total of six subtopics. So I'll begin with the definition of decision support system (DSS). So, based on the chosen article, decision support systems are interactive computer-based systems designed to assist decision makers in handling complex problems. And second, description of the chosen dataset. So, the chosen dataset of our project is IRIS dataset, as it is a renowned collection in machine learning consisting of 150 samples of iris flowers categorized into three species. Firstly, Iris santosa, second Iris versicolor, and third Iris virginica. So here, techniques used such as decision trees and random forests are integrated into the DSS project to provide clear and actionable classifications. Next slide. So here, case study is between the IRIS dataset and decision support system. So let me explain the brief connection between both of it. The IRIS dataset provides structured, interpretable features that DSS can analyze to generate decision rules and automate classification tasks. The dataset highlights the importance of feature selection, showing the attributes like petal width, and petal length are crucial for accurate classification. Then, this case study underscores the connection between data analysis and DSS to improve classification accuracy of the IRIS dataset using random forest and J48 decision tree machine learning models. Next slide. So here, let me explain briefly about decision trees techniques and random forest techniques. So firstly, trees are widely used machine learning algorithms in DSS for classification and regression tasks due to their simplicity and effectiveness. Then these trees divide datasets based on attribute values, forming a tree structure where each node represents a decision criterion and each branch corresponds to an outcome of that criterion. And next is random forests. Random forests extend decision trees by utilizing an ensemble learning approach to enhance accuracy and robustness. A random forest comprises multiple decision trees, each trained on a different subset of the data and features, ensuring diverse models. Next slide. So here, let me just give a brief explanation about the comparison of iris dataset attributes with decision tree and random forest techniques. So firstly, the attributes of the iris dataset interact uniquely with decision tree and random forest techniques. Decision trees use features like petal length and petal width for straightforward and interpretable rules, while random forest balances the use of all attributes by averaging results across multiple trees. Sepal dimensions are less influential in decision trees but gain representation in random forest due to its random feature selection. Together, these techniques leverage the dataset's attribute to improve classification accuracy, with decision trees offering clear decisions and random forests providing robust aggregated predictions. Thank you, and I shall pass to my next team member.
Thank you, Kamalarsi. Let's look into the methodology used in this project. So this project follows the Simon model, which divides the decision-making process into 4 phases, which is intelligence, design, choice, and implementation. This structure helps us to improve the classification accuracy of iris dataset using the random forest and J48 decision tree models. Let's look in detail into the each phases. So the first core phase involved in this methodology is intelligence phase. In the intelligence phase, we focus on identifying the problem and gathering the data. So the iris dataset is analyzed to understand its structure, which includes the features like sepal and petal dimensions. We will also look into the issues overlapping features that affect the model performance. This phase also helps us to gather information on the pre-processing techniques, which is like hyperparameter optimization and ensemble learning, which will guide the next step. The second phase will be the design phase, where we will develop and test the solution. We experiment the pre-processing models like normalization, feature scaling, and feature selection to improve the data quality. We also work on the optimization models by tweaking hyperparameters like the number of trees in the random forest, pruning the methods for J48. Additionally, we explore the ensemble methods to combine the best features of both models. We also will evaluate these approaches using metrics like accuracy, precision, recall, and F1 score. The next phase will be the choice phase. In the choice phase, we will select the best solution based on the evaluation result from the design phase. For example, if let's say a random forest with 100 trees and a maximum depth of 10 gives the best result, it is chosen as the optimal model. Similarly, if let's say we select the best pruning method for J48, then we will also decide on the best ensemble method to boost the accuracy will be the J48 model. The chosen solutions are those that give the highest classification accuracy while being efficient. So the last phase is will be the implementation phase, where in the implementation phase we'll be putting the chosen solutions into practice and test their effectiveness. In this project, we will build and test both the optimized random forest and J48 models using Python and tools like RapidMiner. We will test the prototype and these models with the iris dataset to see how well they are performed in real-world scenarios. The result will also be compared with the baseline models, and a detailed report will show how these methods improve the decision making. All right, let's look into the system analysis and design. So we'll look into the flowchart of this entire project. So the flowchart attached here shows the steps to improve the classification accuracy of the iris dataset. Let's walk through the main steps. First, we load the dataset and check for any issues, fixing them if it is necessary. And then we'll check for missing values and fix them to check on the outliers. And then the data is normalized and we will select the most important features. Next, we split the data into training and testing sets where we will train the model and adjust settings if needed. After training, we evaluate the model's performance using accuracy, precision, and recall. Finally, we will fine-tune the model and save the results. I shall pass to the next team member.
Thank you, Kak Dayani. So next, I will be presenting on the inference diagram of the system. Okay, so basically the inference diagram represents the process of classifying iris flowers based on the data set into three different species, which is Iris certosa, Iris versicolor, and Iris virginica, based on their physical features using two machine learning models, which is the decision tree and the random forest. So at the top of the diagram, there is the features node representing four measurable characteristics of the iris flower, which is the sepal width, sepal length, petal width, and petal length. These features are actually fundamental inputs used to predict the species of flower. And these features are actually divided into two distinct groups to explore different decision-making alternatives. The first is the alternative A, which is the sepal dimensions, focusing on the sepal width and sepal length as mentioned. And the alternative B is petal dimensions, focusing on petal width and petal length. So each of these features is then passed into a decision tree and random forest models, ensuring that these features contribute into a final decision making. So the decision making models, such as the decision tree model and the random forest model, are represented as diamonds, highlighting their roles as key decision-making processes. And these models actually analyze the input features and apply their algorithm to classify a flower into three different species. So the decision tree follows a hierarchical structure where decisions are made at each node based on the features thresholds. For example, if the petal width is less than 0.6. And it prioritizes the feature with the most discriminatory power and generates a single path to a classification. On the other hand, the random forest model is an assemble method that builds multiple decision trees using subsets of feature and data and aggregates the predictions of individuals tree to make a more robust and accurate classification and accounting for variations in the data set. So the outcomes, which is represented in the bottom of the diagram in circular notes, are the iris certosa, versicolor, and virginica. This outcome represents a final classification results, and the both decision and random forest model are connected to all three species, indicating either model can classify any of these three outcomes based on the feature data. The connections demonstrate that the model provide probabilistic and deterministic predictions of each species. So the next is the AHP model. So for this diagram, on the beginning of the diagram, we have the goal, which is the primary objective, and this represents the select the best machine learning model for this iris classification. And then we have the criteria, which is the key factors influencing the decision, which is the accuracy, interpretability, training time, scalability, and robustness. And we have the alternatives, which are the decision tree model, random forest model, and each model is evaluated against all criteria. And we have the outcomes, which are all the possible results of the classifications, which is the iris certosa, iris versicolor, and iris virginica. This hierarchical structure helps visualize how the goal cascades down through criteria and alternatives, ultimately leading to a classification outcomes. That's all from me for this presentation. I shall pass to my next team member.
Next, next I will presenting decision table. So let's look how we classify three types of iris flowers, certosa, versicolor, and virginica, based on the features, petal, and sepal measurements. First, Iris setosa has the smaller petals with the petal length of 1.9 centimeter or less and a petal width of 0.6 centimeter or less. Its sepal size overlaps somehow with the other species. Next, Iris versicolor is the intermediate in size. The petal length range from 3.0 to 4.9 centimeter and its petal width is between 1.0 and 1.8 centimeter. The sepals are slightly larger with a length between 4.9 and 7.0 centimeter with between 2.0 and 3.4 centimeter. Finally, Iris virginica has the largest petal with a petal length greater than 5.0 and width greater than 2.0 centimeter. Its sepals are also largest with a length between 4.9 and 7.9 centimeter with a width between 2.2 and 3.8 centimeter. This specific measurement make it easy to distinguish between the special and the essential in building classifier like decision tree or support vector machine for analyzing inside data. Next, for the production rules, the decision-making rules make classifying iris flowers straightforward and transparent. These rules are expressed as simple as if-then-else statement. They are derived from the part of decision tree which make it the process easy to follow and understand. Here's the rule of classifying the iris species. For the iris setosa, the petal width is 0.21 or less. The species is Iris setosa. For the Iris versicolor, if the petal width is between 0.21 and 0.67, the petal length is 0.66 or less, the species is Iris versicolor. If the petal width is between 0.21 and 0.67, but the petal length is greater than 0.66 and the petal width is also greater than 0.58, it's still Iris versicolor. Last, for the Iris virginica, if the petal width is greater than 0.67, the species is Iris virginica. This simple condition help clearly separate the species and make the classification process transparent and interpretable. Next slide. For the decision tree, it consists of the G48 decision tree. It consists of 7 nodes and 4 leaves. It begins with a split on petal width less than or equal to 0.6, where all the intended satisfying conditions are classified as Iris setosa, making it one of the leaves. If petal width is more than 0.6, the tree split on the petal width less than or equal to 1.7, it leading to further refinement. With this branch, if the petal length is less than or equal to 4.9, the classification is Iris versicolor, forming another leaf. If petal length is more than 4.9, the tree evaluate petal width less than or equal to 1.5, where the true leads of classification Iris virginica and false lead to Iris versicolor, both which are leaf. On the other hand, if the petal width is more than 1.7, the classification is Iris virginica, also a leaf. Each node represents a decision and the tree refines classification on the leaf. Next slide. Okay, this is the G48 decision tree fine-tuning hyperparameter. The tree diagram represents a G48 decision used to classify the iris dataset based on the feature like petal width and petal length. The tree has 6 nodes and 4 leaves. The root node split sample using petal width. If it is less than or equal to 0.2033, the sample is classified as Iris setosa. For the petal width more than 0.2033, further split occur. If the petal width is less than or equal to 0.669, the next decision is based on the petal length, classifying sample as Iris versicolor if it is more than or equal to 0.661, or the Iris virginica if it is less than 0.661. For the petal width more than 0.669, the sample are classified directly as Iris virginica. That's all from me, and I will pass it to the next presenter.
All right, thank you so much. And now I'll be continuing on the result of this project. Basically, this table shows a clear comparison of the decision tree and also the random forest together with the fine-tuning hyperparameters result. The first one is the training accuracy. The decision tree achieved a good training accuracy range, indicating that it effectively learns better in the training data. However, this range also suggests potential overfitting as it might be excessively fine-tuned to the training data. On the other hand, Random Forest achieved perfect training accuracy, which is 100%, showing its strong ability to learn complex patterns due to the assemble of decision trees. This reduces the likelihood of individual tree biases. The second one is cross-validation accuracy. Both models have the same cross-validation accuracy, which is 94.67%, indicating they generalize similar on unseen data. This metric demonstrates that random forest higher training accuracy does not lead to overfitting, which is shown by the stable cross-validation performance. Third is the percentage split accuracy. Decision tree shows a slightly lower accuracy, which is 88.89%, indicating some struggle with generalization when the training set or the testing split is fixed. But Random Forest outperformed J48 in this metric with 91.11%, showcasing a better handling of variability in data splitting. Fourth is mean absolute error. Decision tree has a higher error range, reflecting less precise prediction compared to the random forest, where it displays a significantly lower mean absolute error, demonstrating its higher precision and reduced average prediction error. Fifth is root mean square errors. Decision tree higher values suggest a greater difference between actual and the predicted value. However, random forest lower root mean square error indicates a superior performance in minimizing prediction errors, showcasing its effectiveness with 0.0578 value. And finally is confusion metric accuracy. Disease tree struggles with misclassification, particularly between the Iris versicolor and Iris virginica, due to its simpler structure. However, for random forest, fewer misclassification benefiting from the averaging of multiple trees that reduce the errors of individual weak learners. Next slide. So to conclude, while J48 decision tree is effective and easy to understand, the random forest model provides a better choice for the IRIS dataset. It performs better in almost every way with higher accuracy, fewer errors, and better handling of tricky classifications like for the IRIS versicolor and IRIS virginica. Random forest is also more reliable because it uses many trees working together, making it less likely to overfit and more consistent with different data splits. Since the main goal is to achieve an accurate and reliable result, Random Forest is the best model for this IRIS dataset. That's all from us. Thank you so much.